Good morning students, I am your Nagini ma'am. Today I am going to discuss about the packing efficiency for BCC students. In the last class I discussed you packing efficiency for simple cubic unit cell. Clear students? Now in today's section I am going to discuss about the packing efficiency for BCC. So first of all, what is BCC students? BCC contains students 8 corner particles. So 8 corner particles, and there is a one particle at the center of the body students, and there is a one particle at the center of the body. Clear this one? Center of the body. Now take diagram students, BCC diagram. This is the BCC diagram. Total 8 corner particles will be there. 1 2 3 4 5 6 7 8, and there is a one particle at the center of the body. So this is the body centered particle. Clear? Body centered particle students, and this one is corner particles. Clear this one? So total 8 corners, so plus one particle is present at the center of the body students. So that is the BCC. Okay, now I'm going to calculate the packing efficiency for BCC students. So again I'm taking the one simple cubic unit cell students. This is simple cubic unit cell. See this diagram. Now I'm taking the this particle students, this one and this one body centered particle. These particles are nearer to each other, touches with one another students. So that's why I'm taking here this particle shape is sphere now. So already we know that the particle is considered as sphere, and this particle also it is considered as a sphere students, and this particle also it is considered as a sphere students. Are you understanding? So I'm taking these two particles and this one. So please join this line students. Body centered particle and corner particles. Okay, like this. Join. Now here I'm taking the one face diagonal students here. Okay, and see students, this is the A, B, C, D. Okay now, so I'm representing these points A, B, C, D students. So from the triangle, what we can take students, from the triangle A, C, D, I'm taking first of all A, C, D triangle. Clear this one? This is one line students. This is okay, this triangle I'm taking, this one. Okay, ACD. So from here to here radius R, here to here radius R, R, correct? So here see students, this is R, and here R, here R, here R radius. Clear? So total how many radius? R plus R plus R plus R, total 4R you will get students. Okay, first I am taking the triangle ACD. So from the triangle ACD students, what we can write? I want to calculate first atomic radius. Okay, atomic radius I have to find. So from the triangle ACD, what we can write students? AD square is equal to AC square plus CD square students. AD square is equal to how much students? Total 4R kada. So AD value 4R, R plus R plus R plus R whole square, 4R whole square. 4R whole square, and AC square is equal to AC square as it is, take students, AC square plus CD square. Okay, CD square is how much students? It is the edge length A kada, and here also edge length A, from here also edge length A students. So that's why its edge length is A square, but AC is not the edge length students, it is the face diagonal kada. So that's why first we have to find the AC value, then we can find the radius students, atomic radius. So that's why I'm going to calculate first AC value. So that's why for that sake I'm taking the triangle ABC. Okay, this triangle I'm taking, this one. Okay, this triangle ABC. So from the triangle ABC students, what we can write? AC square is equal to AB square plus AB square plus BC square we can write, correct? AC square is equal to AB square plus BC square. So AC value we have to find, AB value A, BC value also A. So that's why A square plus A square, you will get AC square is equal to how much students? 2a square. So this value here substitute nana. AC square is equal to 2a square na. So this value please substitute here. So then what you will get, students? 4r whole square is equal to, so that means just you write this is the equation 1, this is the equation 2. Now substitute equation 2 in equation 1. So then what you will get, students? Equation 2, AC square is equal to 2a square. Then you will get 4r whole square is equal to, 4r whole square means 16r square is equal to AC square means 2a square plus a square, correct? So then you will get 16r square is equal to 2a square plus a square, 3a square. Then r square is equal to 3a square by 16. Then what you will get, students? R is equal to square root of 3a square by 16. Yes, then r value how much, students? R is equal to root 3 into a square root a, 16 square root is 4. So r is equal to how much, students? Atomic radius root 3 into a by 4, students. Clear? This is the atomic radius completed. Now I am taking the first of all the volume of the unit cell. What is the volume of the unit cell, students? Volume of the unit cell is equal to a cube. Okay, next the volume of one particle, volume of one particle is equal to how much, students? 4/3 per cube, correct? So volume of the unit cell, because unit cell is which shape, students? Its shape is cube na, so that's why I'm taking the volume of the cube is equal to a cube formula. Hence I'm taking the volume of the unit cell is equal to a cube. Volume of one particle is equal to 4/3 per cube, students. So that's why I'm taking the actually volume of particles shape is which one, students? It is a sphere na, so that's why volume of the sphere is equal to 4/3 per cube na. So the total number of particles present in the BCC, the number of particles per unit cell. Okay, now how many particles there, students? We have to find it, the Z value. So the number of particles per unit cell, Z value is equal to 2, students, per BCC. Yes, before we discussed this one, the number of particles per unit cell Z is equal to 2. That means nothing, students. Here BCC how many particles? 8 corner particles, and 1 particle is present at the center of the body na. So 8 corner particles means 8 into, and 1 by 8 is its contribution, plus 1 body center particle, its contribution is 1, correct? 8 will get cancelled, then you will get 1 plus 1 is equal to 2. This is a Z value, students. Okay, the number of particles per unit cell. Then the total volume occupied by the particle. Okay, then the total volume occupied by the particles. How much, students? Occupied by the particles, how much? 2 into 4/3 pi r cube, because how many particles are there per unit cell in BCC? 2 particles, 2 into 4/3 per cube. Now we have to find the packing efficiency, students. How to find it, now we will discuss. So what is the formula, students? Packing efficiency is equal to what we can write. See here, packing efficiency is equal to volume occupied by the particles, volume occupied by the particles divided by volume of the unit cell, into 100%, students, into 100%. So then volume occupied by the particles, how much, students? Volume occupied by the particles, 2 into how much, nana? 2 into 4/3 per cube na. So that value have to take 2 into 4/3 per cube, 2 into 4 by 3 pi r cube, divided by volume of the unit cell. What is the volume of the unit cell, students? Volume of the unit cell is equal to a cube na. So that value here substitute, students. Volume of the unit cell, so what you will get? A cube into 100%. Clear this one? Into 100%. Now this is the packing efficiency is equal to 2 4s are 8, by 3 pi. R value how much, students? R value in BCC we calculated na, R is equal to radius root 3 into a by 4. So that value here substitute, students, pi root 3 a by 4 whole cube by a cube into 100%. Okay, packing efficiency is equal to 8 pi root 3 whole cube. What is root 3 whole cube, students? Root 3 whole cube means, here see, root 3 into root 3 into root 3, correct? 3 times we have to multiply. Then root 3 into root 3, 3, 3 into root 3, 3 root 3, correct? So here substitute 3 into root 3, and here a cube as it is, take, students, by 3, here 3 already there, here 4 cube means 64, 4 fours are 16, 16 fours are 64, into a cube in the denominator into 100%. Now this a cube 3 will get cancelled. Clear, students? Then packing efficiency is equal to 8 in 64, 8 times 8 8s are 64. Then you will get pi into here root 3 in the numerator, in the denominator only 8 into 100%. Clear this one? Pi into root 3 by 8 into 100%, students. Then packing efficiency is equal to pi value 3.14, root 3 value, students, 1.732 into 100% divided by 8, nana. Okay, then if you calculate this one, you will get BCC value, nana. BCC value 68% you will get, students. How much you will get, nana? 68%. BCC value how much you will get, students? BCC 68. This is the packing efficiency. That means this much percentage of the space occupied by the particles in the BCC unit cell, students. Clear this one? Okay, so 68% volume is occupied by the particles in BCC, students. Now we have to find the empty space. How to find it, students? Empty space, see here, empty space is equal to 100 minus 68%, students. That means 100 minus 68, how much, students? This value 32%, correct? So the 32% is the empty space. 68% space is occupied by the particles in the simple cubic, in the body centered cubic unit cell, students. Clear this one? Okay, thank you, students. I hope you like this video. Please like, share, comment and subscribe my channel, students. Thank you, students.